Welcome to my video on Euler's method for BC calculus. Now the name Euler may or may not be familiar to you depending on how well you remember your geometry. This is the person that this method is named after is called Leonhard Euler. He was a Swiss mathematician, lived in the 18th century. If you think of Stephen Hawking or maybe Einstein, this guy was right up there with him as far as his ability to uh, do stuff with math. He was one of, if not the most prolific uh, math publishers of all time. He's had all kinds of things credited to him. In your study of high school math, you may have heard the term the Euler line in geometry as it relates to circumcenters of triangles, meaning the uh, incenter, orthocenter, circumcenter, and centroid. If you create all of those lines on the same triangle, those 4 points of concurrency all sit on the same line. That was the Euler line in geometry, and what we're going to be looking at now for BC calculus is how you can use this method that Euler created and solve or at least approximate solutions to differential equations. Now in an AB course, you typically are going to see something with slope fields, which would show you a family of solutions for a particular differential equation, and you would have studied how to solve separable differential equations. And those types of equations, the separable ones I'm specifically referring to, are what we would think of as an ordinary differential equation or a linear differential equation. And by that I mean that if any coefficients that you might typically think of in a differential equation could be written with a function with respect to x only. Well, just like you see in a lot of other things in algebra courses, there are a whole lot of other things in math that are simply not linear. And it's the same thing with differential equations as well. And a lot of differential equations that are not linear, you are not able to try to solve them using your typical approach. A lot of people would typically want to just try to solve it using some kind of algebraic analysis. We're trying to solve for x, so to speak. But in a lot of nonlinear differential equations, that simply isn't possible. And so the only way that you can identify where a solution may or may not be is really to do kind of a numerical approach with slope fields, and that will get you at least an approximate solution of the differential equation. Now, moving on to what we see here, we have two graphs. They're referring to the same thing. Let me just kind of explain what is what here. So we have a curve on the first one, and what we would think of as an overestimate for the curve. We have these points, P0, P1, P2, and so on. So starting off, we are kind of here at P0. What we would do at that first point is we would want to know what is the slope of the tangent line here. Tangent line. And you can find that out using a lot of other methods that you've seen in calculus so far, but essentially what we're going to do is we want to be able to figure out what is the slope of a tangent line there, and we could kind of take that and let's see, we would have something that kind of goes like this. Okay, and maybe that may not be completely accurate, but that's essentially what we're doing is we're finding the slope of the tangent line. Now, when we were looked at slope fields, we kind of focused on just the little segments, and that's essentially what we're doing here. We're looking at the little segments of the slopes of through each point, so that way we can identify, well, if I know the slope at this point, I can use that to get to my next point. So I go here, I go here and I'm using the slope, and then we would kind of repeat the process. We would get another kind of slope of a tangent line, like so, and we would use that one to go to the next point and the next point and so on. And ultimately, what we wind up getting would be the curve of the over approximation with the actual solution of the function. So what here that we have is the smooth curve. This is your exact solution. Whereas this pieced together bit here with all of the line segments, that would be your Euler approximation. So there is going to be a margin of error. You're not going to get the exact function or the exact solution, but in a lot of times you'll be close enough. And Euler's method is probably, it kind of hit the spotlight a little while ago in that movie Hidden Figures. There was an actress, Taraji Henson, I think it was, who played Katherine Johnson at NASA, and she was kind of working with this guy who was played by Jim Parsons from Big Bang Theory, and they were trying to figure out how do we solve this problem to get these, put these guys into orbit and be able to get them home safely. And they were banging their heads against the wall. They couldn't find out the solution. And, obviously it was dramatized for the movie, but they're like, well, what if we use Euler's method? It's ancient, but it may work. And yeah, it does. This is going to give you a solution that you can get close to without actually being, exact on. And obviously the margin of error has, you have some play in how much the margin of error is going to be. But that's what we're kind of looking at what this, you know, paragraph here is kind of talking about. We're looking for that local linearity that we create with the slope field, because if you zoom in on any curves close enough to a high degree, it's at a certain point, it's just going to, it's going to be indistinguishable from its derivative, from its slope of the tangent line at that point. And when we have those and we have enough of them, we can get enough points to approximate what the actual curve is going to be. And that is really what we're going to be looking at when we talk about Euler's method. Now, here we have a very simple differential equation. And I know it's a differential equation because we have the dy over dx is equal to y in this case. And they're giving us our initial conditions. My initial condition when x is 0, y is 1, and they're giving me some step that they're changing it by, delta x, okay? And what we want to be able to do is we want to be able to create a table of a table based off of the differential equation that we have, so that way we can kind of approximate what our solutions are going to be. Now, here we're kind of looking at, you can kind of look at your equations similar to this, where we say y1 is going to be equal to, no, I don't want to write it this way. Give me 1 second, let me change that. We can write it as the derivative of y times delta x plus the initial y value, y naught. And using that information, we can kind of, get to what our y values are going to be where we are approximating them. So let's go ahead and fill in the table and see how we're going to use Euler's method to create an approximation for this particular differential equation. Now this is a linear differential equation. This is easily solved using these separation techniques that you would have seen previously in calculus. But let's go ahead and apply it using Euler's method. Now the slope, okay, so starting here, we know the initial conditions are when x is 0 and y is 1. Now in this case, because of the differential equation that we have, dy over dx is equal to just y. In this case, y and our slope are going to be the same thing, because that's how you create the slope field, is you just, pick numbers for x and y and substitute it into the expression for the differential equation and see what you get. So in this case, all of the y values and the slope values are going to be the same. Now the delta x being 0.1 kind of makes things a little easy on us here for the x column. We can just kind of, the change in x is going to increase by 1 each time, so we can kind of just fill these in here, stepping them up by a tenth each time. Now the rest of them aren't going to be quite as easy to get on their own. And I'm going to work a couple of these out just to kind of give you the idea. Then I'm going to pause the video so that way you don't have to actually see me write everything in. It's just a little time consuming. But let's go ahead and see what we have here. And the one thing that I will kind of explain is that the column that has tangent line and the column that has x plus delta x, I really wish these were reversed. I really wish those were reversed because the tangent line is easier to get once you know what your y value and what your x value are going to be. But anyway, so in this case, x plus delta x, starting it off, that's just taking our initial value plus delta x, 0.1. So our initial x value is 0, and 0 plus 0.1 is just going to be 0.1. So that's really all I'm looking at here for my my x value. Okay, so I'm going to take those values. I'm going to looking at this equation that we have. Oh, give me 1 second. Having a phone emergency. Forgot to turn off an alarm that I had set. So now that we've identified, from our initial conditions, x and y are going to be these numbers. We understand that the slope is this example is going to be the same thing as your y value, and we're able to identify what our x value is going to be. We could take that and simplify that so where our tangent line in this case would look something like, y is equal to x plus 1, x plus 1. So if I take the x value that I had, the 0.1, and I add it to the 1 that's already there, 0.1 plus 1, we wind up getting our new y value of 1.1. Now, in case I think I get distracted by my phone. I'm not entirely sure I explained that as well as I would have liked. Why am I plugging those in the way that I am? And that is based off of this right here, where we're saying the derivative of y times delta x plus y naught. So in that case, where we would look at it, well, let me do that up in the blank spot where I have a little more space to write. The y value that we're looking for is this right here. And in this case, y prime and the slope are the same thing because that's the derivative of the tangent line. So I would say the new y value is going to be equal to the initial y value, or not the initial, but the derivative of y times delta x plus the y naught value. Not y naught, but anyway, so subscript of 0, we read it as naught. So the derivative of y in this case is 1. Delta x in this case is 0.1. And y naught in this case was the initial value of 1. And when you say 1 times 1.1 plus 1, we wind up with the 1.1 that we get here for our new y value. Well, let's go back, or let's go to our next row in our column here in our table and see what we wind up with now. Well, that new y1 value that we got, that goes here for our y number. Okay, so now I'm in the row where it says P1, and so the x value, that's easy to get because of the step value that delta x was given as just being 0.1. But the y value we have to calculate that a little bit. And those are where our solutions are going to really wind up being. So that's where we're going to say, okay, well, next is this. What's y going to be? When our input is this, what's our output going to be? Now, again, in this particular example, the slope, the y prime and y are going to be the same thing. So I get a 1.1 there. Now, looking at this particular one, uh, where it says, and again, I'm going to do the tangent line one last. Okay, so x plus delta x, I'm just looking at this x here in this row, this x plus delta x. So 0.1 plus the delta x of 0.1 gives me a 0.2 now. So now that I have that, by having that 0.2, now we have all of the x and y numbers that we would need to figure out what our new y value would be. So again, I'm looking at the equation y is equal to y prime times delta x plus y naught. And when I do that, I'm going to get y is equal to delta, or y prime in this case is 1.1. The delta x is going to still be 0.1, so 0.1 plus the, now in this case, we're not going to the y naught. We're not going to go back to the initial y value. We have to go to the y value that we created from the last step. So this new y value here of 1.1 is what I put here. So 1.1 times 0.1 plus 1.1 is what our new y value will be, which in this case will be 1.21. Now at this point, I'm going to encourage you to pause the video and see if you can fill in the rest of the table on your own. And that's exactly what I'm going to do. I'm going to pause the video so I can fill in the rest of the table so that way you don't have to listen to the, because filling in the rest of the table is just a rinse and repeat phrase at this point. So go ahead and pause the video and I'll do the same. And click play when you're done and see if you compare my answers to your answers, how well you did. All right, so hopefully the pause of the video for me to take the time to fill in the table wasn't too disconcerting. And again, you should have paused the video to fill this in before you saw what the final answers here were going to be. But looking at the far right column where it has the new y values, those are the outputs that we're getting based off of a particular input for our function or for our differential equation. And the two columns that are on the far left where it says x and y, those are where we would get our approximate solutions from. Okay. Now, we're going to see this again later on, but if you really want to, you can look at the table of values on a calculator, because the differential equation that we started with, dy over dx being equal to y, that is the same thing as y being equal to e to the x power. That is what the uh, specific equation that the slope field would model come from. And if you look at, if you type the y is equal to e to the x power and you look at the table of values of that function on your calculator, you're going to see that the numbers that we were getting for the 0.1, 0.2, etc., the y values, they're going to be close. They're not going to be the same, but they will be close. And that's essentially what we're doing with Euler's method. Now, could we have come up with those numbers on our own? Yeah, we could have solved the differential equation by itself and then moved on and got our values that way. But this is a simple differential equation that we're using to try and introduce the process of how you use Euler's method to approximate a solution for points along the curve. So we're going to go ahead and stop this particular video here. We'll finish the rest of it in the rest of the notes in a separate video. Until then, guys, thanks for watching and take care.